Here's an equilibrium problem. We're given a balanced chemical equation, a value of K. This is Kp, and our amounts are given in partial pressures. And so what we want to find is the equilibrium partial pressures. We'll do our ice table and put our initial amounts. We assume that the reaction is going to go forward in the forward direction towards the right. So we're going to lose X and X moles each of these reagents and gain 2X moles of our products. Equilibrium amounts are always initial plus the change. So we have 1 minus X, 1.03 minus X, and 2X. Our value of Kp, which is 50.2, is equal to the partial pressure at equilibrium of Hi. That's going to be squared over the partial pressure of I2 raised to the first power, and H2 also raised to the first power. Right, we can input our values from the equilibrium table, the ice table. So we have 2X quantity squared over 1 minus X and 1.03 minus X. And this is all equal to 50.2. So we have 50.2 is equal to 4X squared, because this is 2X times 2X. And we have 1 minus X, 0.03 minus X. Alright, 50.2 is equal to 50.02 over 1, and this allows us to see easily how we cross multiply to get 50.2 times 1 minus X, 1.03 minus X is equal to 1 times 4X squared. Now for this quantity, we're going to have to use the FOIL method, multiplying the first, the outer, the inner, and the last quantities together. If we do that, we would get 1.03 minus 2.03 times X minus a minus plus X squared is equal to 4X squared. Now we're going to go through and multiply each of these values by 50.2. So we have 51.706 minus 101.91 times X plus 50.2 times X squared. And this is equal to 4X squared. Collect like terms, and we want to put this in the form of ax squared plus b plus bx plus c is equal to 0. Okay, we're not going to be able to make any simplifying approximations because the value of k is just simply too high. And these values x are not going to be insignificant compared to this initial value. So we're going to have to use a quadratic equation. Alright, so we're going to collect our like terms. So we have 50.2x minus 4x squared for our first value, a. So 46.2 times x squared. And the rest we just rewrite. And this is all equal to 0. So we see that this is the value of A, this is B, and this is C. And we're going to apply the quadratic. X is B plus or minus the square root of B squared minus 4AC. And this is all over 2A. when we solve the quadratic, we're going to get two roots, and we'll see that one of these roots is not going to make any physical sense, and therefore the answer will be the other root. Alright, so let's do this. We have x is going to equal minus b, which is minus a negative 101.91. So we have positive 101.91. And we're going to add and subtract this quantity here, 101.9, oops, decimal point is in the wrong spot, 101.9 quantity squared, because that's b squared, minus 4 times a, 46.2, and c, 51.706. It's a bit awkward, but we can do this. Alright, and the whole thing is over 2a, which is 2 times 46.2. Alright, we crunch this number under the square root sign out, and what we get is 101.9 plus and minus the square root of 828.3, and this is all divided by 2a. So this comes out to be 101.9 plus and minus the square root of this entity is 28.78. This is all over 92.4. Alright, so what we end up with is two values of x. One value of x, we have x1 is equal to 101.9 plus 28.78 divided by 92.4. This is equal to 1.414, and x2 is equal to 101.9 minus 28.78 divided by 92.4 equals 0.7913. Okay, now that we have our two values of x, let's look back to our initial ice table and see which one of these is going to make sense. Well, only the smaller value will make sense because our initial value of our partial pressure is 1 and 1.03, and if we can't subtract 1.414 because that would give us a negative pressure, which is just nonsense. So we're going to ignore this value and recognize that this root is going to be our value for x. Okay, we look up to our table now that we have x and answer the question. The question is, what are partial pressures of the reactants and the products? So we can plug x into our values. We have H2 is going to be 1.00 minus x. So that's 1.00 minus 7. Come on. 0.7913. We can only go out to the hundredths place as far as sig figs. So this is going to be equal to 0.21. I2. Actually, these are not concentrations. So this is the pressure of H2. Pressure of I2 is equal to the pressure of I2 is 1.03 minus x, 1.03 minus 0.7913. And when we go out to the hundredths place as far as sig figs, this is going to be 0.24 atmospheres. And finally, our partial pressure of HI at equilibrium is 2 times X, which is 2 times 0.7913. And if we go to the hundredths place, we find that's 1.58 atmospheres. Okay, kind of a long slog to get to the answer, but that's what it is. We could not make an approximation at this to make the math easier, because as we see, these values of X are not insignificant compared to what they're being subtracted from. So we cannot make the approximation that this X is insignificant compared to this value. So we're stuck with using the quadratic equation.